Example 1. It's cloudy 1 in 5 days. So clouds 1 in 5 days. Okay, so what that means is if you picked a random day, the probability, the chances of clouds are 1 in 5. Okay, it rains 1 in 7 days. 1 in 7 days. So if you picked a random day, the chances of rain, the probability of rain is 1 over 7. This is approximately correct for, the Northeast. Okay. Now, the question, what are the chances of rain on a cloudy day? Chances of rain on a cloudy day. So let's pin down exactly what we're asking for. We're asking for, if you picked a random day and I told you that it's cloudy, then what are the chances of rain? Effectively, we're asking, what's the probability of rain given clouds? And now we can just apply the formula, which says that this is a conditional probability. We need to update the probability of rain from 1/7 to take into account the new information that it's a cloudy day. Okay. So this is the probability of rain and clouds. So intersection means and clouds, divided by the probability of clouds. Now you can just take this as a definition of conditional probability, even though we derived it. Okay. And, what is this? Well, it looks like we can't compute it. We know the probability of clouds. We don't know the probability of the intersection until we think about it a little bit in the real world. You can't have a rainy day without clouds. So the situation looks like this. Here are all days. And then here are the cloudy days. Okay. And the rainy days are a subset of the cloudy days. Okay. So this means that rain is a subset of clouds. So rain intersection clouds, so the rainy days intersection the cloudy days is exactly equal to the rainy days, rain. So this is the probability of rain divided by the probability of clouds, which is equal to 1 over 7 divided by 1 over 5, which is equal to 5 over 7. Okay, interesting. So a random day, the chances are about 15%, 15% that it's, a rainy day. But, if you tell me that it's a cloudy day, then on roughly 70%, 5 out of 7 cloudy days, it rains. 70% of cloudy days are rainy. So giving me this additional information that it's cloudy significantly changes the chances of rain. And we are all familiar with this phenomenon in the real world. On cloudy days, you're much more likely to get rain than on a random day. Okay, let's do another example. Example 2. Roll a pair of dice. Okay, so now let's think about the outcomes. The first die can be 1, 2, 3, 4 up to 6. The second die can be 1, 2, 3, 4 up to 6. So a useful, convenient way to represent the outcomes, is using a grid. So I'll draw it like this. So this is die 1, I'll call it D1. This is die 2. Okay, it can be 1, 2, 3, 4, 5, 6. Die 2 can be 1, 2, 3, 4, 5, 6. And so what are the possible outcomes? The possible outcomes are all the grid squares, all the grid points. So here are the possible outcomes. Okay, I'm getting good at drawing little dots. Look at this. Okay, now, if you do the outcome tree, so the first die can have one of 6 outcomes, and then for each of those, you can branch out another 6-fold. Okay, so you'll get 36 total outcomes, 6 times 6, and you'll see that the probabilities are 1/6 times 1/6, and it's the same for all the outcomes. So it's a uniform probability space. So it's a uniform probability space. So all outcome probabilities, okay, are 1 over the number of outcomes, 1 over the size of the sample space, because it's a uniform probability space, and you can get this also from the outcome tree. It's 1 over 36. 1 over 36. Okay, let's ask some questions. What are the chances that you roll a sum of 10? Probability that sum equals 10. Okay, so we need to identify the event sum equals 10. The sum equals 10, it can you either get a 6 followed by a 4, a 5 followed by a 5, or a 4 followed by a 6. So let me highlight those outcomes. So it's a set of outcomes. So this is very important. An event is a set, a subset of all the possible outcomes. So the probability that the sum equals 10 is, because we're in a uniform probability space, it's just the number of outcomes divided by the size of the sample space. So this probability is just equal to 3 over 36, which is 1 over 12. Okay, the chances are 1 in 12 that you roll a sum of 10. Let's ask another question. What are the chances that both die are odd? What are the chances that both are odd? Okay, so let's identify the outcomes where both are odd. So both are odd. So here, both are odd. 1, 1, 1, 3, 1, 5. 2, both are not odd. 3, 1, 3, 3, 3, 5. 5, 5, 1, 5, 3, 5, 5. Okay, and if we count up the number of outcomes where both are odd, you see it's clearly 9. So the probability that both are odd is 9 over 36, which is 1 over 4. Okay. Let's compute the conditional probability that the sum is 10 given that both are odd. Okay. So if I'm now interested in the probability that the sum is 10 and I've rolled a pair of dice, okay, and I tell you that both are odd, that's new information. So the probability that the sum equals 10 given that both are odd. Okay, so now this guy we just applied a definition of conditional probability. So mechanical approach to computing conditional probability. The probability that the sum is 10 given that both are odd is just equal to the probability that the sum is 10 and both are odd divided by the probability that both are odd. So this is the mechanical approach. We derived it. It has a frequency interpretation of, when you run this experiment and only focus on the situations where both are odd, because that's, what information you're given, then the frequency, the fraction of those outcomes where both are odd will be this conditional probability. Okay. And now we need the intersection of the sum being odd and the sum being 10 and both being odd. Well, so we need to look at the intersection of these two sets, and there's only one outcome here. And so the probability that the sum is 10 given that both are odd is just 1 over 36 divided by the probability that both are odd. Both are odd is 1/4, 1 over 4. So this is 4 over 36, which is 1 over 9. There. So the chances that you have rolled a 10, if you know that both your rolls are odd, is 1/9, okay, which is slightly higher than the chances of rolling a 10. Okay, it's slightly higher than the chances of rolling a 10. Okay, so exercises. Compute exercise. Compute the probability that both are odd given that the sum equals 10. So this is what we call the transposed conditional. So I flipped the probability you're interested in and the information you have. So now I'm asking you roll a pair of dice and I'm telling you that the sum is odd. What are the chances that both are odd? I'm telling you that the sum is 10. What are the chances that both are odd? Okay. So pause the video for a couple of seconds. 1, 2, 3, 4, 5. And if you're coming back and if you compute it, I'm going to tell you the answer. Okay, so the answer here is, we need to compute the intersection, but that's the same. So it's 1 over 36 divided by, now we need the probability that the sum is 10. The probability that the sum is 10 is 1/12. Okay, so this is equal to 12 over 36, which is 1 over 4. Okay. 1 over 3. Okay, sorry, 1 over 3. 12 over 36, which is 1 over 3. So look, okay, the probability that both are odd is 1 over 4. Now, if you tell me additionally that I'm giving you the additional information that the sum is 10, now the chances that both are odd has gone up to 1/3. So probabilities get updated when you get new information. And interesting, okay, the probability of A given B is not the same as the probability of B given A. In general, okay, do not assume that the probability of A given B is not generally equal to the probability of B given A. Okay. So now let's summarize the mechanics for computing a conditional probability. Okay, so let's erase. And compute and summarize conditional probability mechanics. for conditional probability. Okay. And it's not very different. It's not much more complicated than computing a probability. So, so some people might say, oh, computing conditional probability is very hard, and so on and so forth. It's not. And it's all due to this fundamental formula that relates this conditional probability to the ratio of two regular probabilities. Okay? So the conditional probability is the ratio of two regular probabilities. Because A intersection B is a set, it's an event, and B is an event, it's a set. So if you can compute regular probabilities, you can compute conditional probabilities. Okay? Now, so here's sort of a cheat sheet. Here's a workflow. So the first thing you need to understand is that, you're being asked to compute a probability and you're being given some side information. So you need to sort of realize that conditional probability is relevant. You need a probability and, you are given some side information. For example, what are the chances of rain given cloudy? Okay. What are the chances of a sum being 10 given that both are odd? Okay. So you're asked for a probability and you're given some additional side information. Okay. So the first thing you do, so probability is relevant. Okay. So you need to compute, just like we did, for example, with the dice, you need to compute your sample space, the possible outcomes, and the probabilities associated with them. So figure out the probability space. So this is the samples, the possible outcomes, the sample space, and the associated probabilities. Okay? And you can use the outcome tree method, for example, to get this. So if it's a uniform probability space, things might be easier. Okay? So for example, outcome tree method. Okay? Now, you need to take the question you're asked and identify from within this sample space, what are the sets A and B. So identify the events A and B. Okay. So for example, in our case, we said what are the chances of rolling a 10 given that both are odd. So rolling a 10 corresponded to an event, a subset of 3 outcomes, and both being odd corresponded to a subset, an event of 9 outcomes. So you have to identify the events A and B. Okay. Then you have to compute regular probabilities. Okay. So in the normal way, you compute regular probabilities P of A, P of B, and P of A intersection B. So how do you compute regular probabilities? For each outcome in the corresponding event, you just add up the outcome probabilities. And you know all the outcome probabilities, and you know the events A and B, so you also know the event A intersection B. And then you just apply the formula. Very simple. Okay, the probability of A given B, you set this equal to the probability of A and B divided by the probability of B. Okay, so technically you don't need the probability of A for this guy, but if you wanted the other guy, probability of B given A is equal to the probability of A and B divided by the probability of A. Okay. And it's very important to realize that these two are not generally equal to each other. Okay, so that's the workflow for computing conditional probabilities. It's not really much harder than computing regular probabilities because we have related conditional probability to regular probabilities. That is the entire point of this formula, this definition. Okay, let's erase and do more examples. Now we will do speed erase. Bam, bam.